and or waves in general have a frequency. And when we talk about a frequency, is the number of cycles per second, and the period is the time it takes to complete one cycle. So by just looking at the definition of these two terms, you can see that they're inversely related to each other. So that the frequency is inverse related to the period, and period is inversely related to the frequency. So frequency is equal to period divide 1 over period, and period is equal to 1 over frequency. Okay, so we did this in our last in the last session, so we're not going to belabor this point. So they're inversely related, and it's important for you to remember that. You can work it out because it's not difficult. Again, what we said, that waves transport energy. So you take any wave that you can think about, what it's doing is transporting energy. That's what waves do. They transport energy. And the amount of energy that the wave transport uh, is directly proportional to the amplitude of the wave. So the greater the amplitude, the greater the energy. So so again, when we talk when you have a wave a wave phenomenon is because you have vibration of the particles in the medium. The medium does not move. Okay, the medium does not move, and or the matter in the medium does not move. Okay, all right. So when you have, just in general, if you're outside and you're talking to someone, your vocal cords move, generate the sound. Your particles in the vicinity of your vocal cords are going to vibrate. So as the particles vibrate, they move back and forth, back and forth. So it's not a wholesale movement of particles. Okay, the particles vibrate, and the closest particle to the vocal cords vibrate, and it set the subsequent the particles adjacent to that. It's going to set those particles into vibration, and it's going to cause the vibration of the next particle, until you get a series of vibration, and it's these vibration which um, is the wave phenomenon. So it's not a movement of a wholesale movement of particles. It's due to the vibration of particles in the medium. Okay, if you take a light wave, for example, um, from the sun, we get light from the sun. What happens is you get vibration of charged particles. Okay, the vibration of charged particles, and that generate the electric wave, or the light wave, that generate the light wave. So wave is due to the vibration of particles, not the wholesale movement of particles. Again, the amount of energy that is transported in a wave is related to the amplitude of the wave, and we did show you what an amplitude in the wave pattern looks like. So high energy, high amplitude; low energy, low amplitude. Um, Now we're going to tell you that the speed of a wave in a medium is related to what we call the inertial factor and the elastic factor. Okay, so the speed of the wave, which is you know how fast the wave is traveling in a medium, is related to the inertial factor and the elastic factor. And it's important to understand what these terms mean. So when we say the inertial factor, it means how massive the medium is. Okay. Uh, so the more massive the medium, it resists the movement of the wave. Um, so and the inertial factor is related to the density of the medium per se. So you would say the more dense the medium, the more inertial factor it has. And it is well established that the speed of the wave is inversely proportional to the density of the medium. Okay? The speed of the wave is inversely proportional to the density of the medium. That is, the more dense the medium, the slower the speed of the wave. And this is very important. If once when you do ultrasound, is very important to understand that, because if the medium is very dense, then the sound wave is going to travel slower in that medium. And if the density of the medium is a less dense medium, it's the sound wave is going to speed up. So when you're doing your imaging, you're going to move, your ultrasound is going to move from more dense to less dense to more dense, less dense. So you have to know what's happening to the speed of the wave when it moves from one medium to the next medium. Okay, the speed is going to vary with the density of the medium inversely, right? So the speed is going to be inversely related to the density of the medium, and it is going to be directly proportional to the elasticity of the medium. Okay, so when we talk about the elasticity or the elastic factor of the medium, it is a springiness of the medium. So the more elastic the medium, it will offer less resistance, and the wave will travel much faster. Okay, so two important properties of a medium that affect the speed of the wave is the density and the elastic factor. Okay. All right. So we we stated that the energy of the wave, again, waves are just energy transporting uh, phenomenon. Light wave, ultrasound waves, or sound wave, water wave, any kind of wave that you can think about. What it's actually doing is transporting energy, and the amount of energy that's contained in that wave is proportional to the amplitude of the wave. As a matter of fact, it is directly proportional to the square of the amplitude of the wave. So the amount of energy, the greater the amplitude, the greater the energy. Okay, the relationship is a square, so it's directly proportional to the square of the amplitude. Okay, very important factor. So when we talk about the speed of anything, so we briefly mentioned that the speed of the wave is related to the elastic factor of the medium and the density of the medium. The speed is directly proportional to the elastic factor. So the more elastic the medium, the greater the speed, the greater the density, the slower the speed, because it is inversely related. Now, what is speed? Speed of a wave. Speed as a universal definition. So it's not going to change because of we're talking about wave. Speed is the time it takes to cover a certain distance, and that's a standard definition. So it's the distance traveled per unit time. It's how fast an object is moving. So it's the same definition for a wave. So it is the distance traveled by a given point on the wave in a given interval of time. So you can use the crest and the trough, or the trough and the crest, whatever. But it's the distance traveled by a given point on the wave in a given interval of time. Okay. Um, a simple way of a simple way of looking at the speed of the wave. Um, take the wavelength. We said that the wavelength is the wavelength is a distance. So the wavelength is the distance or the length from crest to crest or from trough to trough. It is the length. So the wave travels that distance. Okay. So the wavelength is from crest to crest or from trough to trough. Remember what we said, the period. The period is the time it takes to complete one cycle. So it is a time traveling from one crest to the next crest. Let me just draw this out so you have a very good understanding. Um, so remember, we when we look at we draw our waves looking like this. When we look at the anatomy of the wave, so this is a crest right here. So let's denote that by C. So this is a crest. This is another crest. This is another crest. This is a trough. And this is another trough. Okay, so remember the amplitude of the wave is the maximum displacement from rest. So if this is the rest position, let's I'll tell you what, let's draw the rest position like this. So if this is your equilibrium or the rest position, so the amplitude is the maximum displacement from the rest position, okay, and the amplitude square is proportional to the amount of energy. So the greater the amplitude, the greater the energy that the wave is transporting. Waves just transport energy. That's what it does. The distance from crest to crest or from trough to trough is what we call the wavelength. So, okay, just think of this as a nice line, straight line. And we usually use lambda to denote wavelength. Okay, so the distance from crest to crest or from trough to trough, that distance is the wavelength. The time it takes to complete one cycle is what we call the period. So the time it takes to travel from crest to crest is the period. Remember what we say, speed is distance over time. So the distance traveled by the wave for one wavelength, so you can write speed like that. So it would be the distance is one wavelength, and then we're going to divide it by the time. Remember the time it takes to complete one cycle, that's the time it takes the wave to travel from crest to crest, is the period. We call that the period, right? Okay. So the speed of the wave is equal to the wavelength lambda over the period p. But remember what we said, the period and frequency are inversely related. So 1 over period is equal to the frequency. So you can write this formula another way, that the speed is equal to the wavelength times the frequency. And this is the wave formula. Okay? So the speed of a wave is equal to the frequency times the wavelength. The speed of any wave is fixed in a medium. So the speed of any wave in a particular medium, it is fixed. It's not going to change. However, if it moves from a less dense medium to a more dense medium, it's going to slow down. It's going to slow down. Okay? All right. So you have to know how this formula is derived. You're going to see it quite often, but you have to know how it's derived. The speed of the wave is equal to the wavelength times the frequency. All right. All right. Now, remember what we said. When you have a wave, or when you scanning, say the heart, you turn your instrument on. The piezoelectric crystals in the ultrasound probe vibrates. That vibration is going to set up a sound wave. The sound wave is going to travel from the transducer or the probe to whatever structure you're looking at. That wave is going to be reflected from the object or the tissue, whatever. Some of the wave is going to be reflected backward to the transducer. The transducer is going to pick it up and it's going to convert that sound wave into an electric signal, and you're going to see that on the screen. That's the image that you see. Some of the wave is going to pass through the tissue and is transmitted. So when we talk about reflection, try and understand what we mean by reflection. When a wave reaches the end of a medium or a different medium, it bounces off and reverses its direction of travel. Essentially, the sound wave leaves the transducer, it hits the structure, and it comes back to the probe. So it's very important to understand what's happening here, because for you to get an image, the sound wave will have to travel from the transducer, hit the structure, and come back to the transducer. So it's going to travel a distance from the transducer to the structure, and it's going to reflect it backwards the same distance. So it's going to travel, the distance twice. It's going to go and come back. So the distance is double. So you have to understand that, because if you're going to calculate the time it takes the ultrasound wave to go to and or just to the structure, you have to remember that it's going to travel, the distance is going to be double, because it's going to move from the transducer to the object and it's going to come back to the transducer. So the distance, it's going to double the distance. Okay. Similarly, if you in a canyon and you shout in a canyon, the way the sound have to travel from your mouth to the canyon wall, bounce off the canyon wall, and then come back to here. So same thing. It's going to travel. The distance is going to be doubled. Okay. So, and you can work out all sort of thing. If you know the if you know the time, you can time it. You can shout, uh, time it, and then when you hear the echo, that means that the sound travels to the cannon wall, come back. So you have the time, the speed of sound in here, so you can calculate the distance of the cannon wall from where you're located. So similarly, when you do ultrasound, you can calculate distance, time, because you know the speed. Remember, we said the speed of ultrasound in soft tissue is 1540 meters per second. You have to remember that. The speed of sound wave in soft tissue is 1540 meters per second. So this is just giving an example. If you're in a cannon wall, if you're in a cannon and you shout, okay, it's gonna, and if the cannon is 50 meters away from you, it's gonna it's gonna travel 50 meters to the cannon wall. It's gonna come back another 50 meters. So its total distance travel is gonna be 100 meters. And if it takes 1 second to go and come back, then the speed is 100 meters per second. So simple math. Again, we are touching this, but the speed, we show you how you derive the speed formula, the sound the sound formula, or the wave formula, where speed is equal to frequency times the wavelength. But if you do a little bit more thinking, a little bit more research, you see that the speed of a wave in a medium is dependent on the density, and we show you that the more dense the medium, the slower the speed, the less dense the medium, the greater the speed. It is also dependent on the temperature. The greater the temperature, the greater the speed. And the more elastic the medium, the greater the speed. So the speed of a wave is inversely proportional to the density of the medium. So the more dense the medium, the slower the speed of the wave. And it is directly proportional to the elastic property of the medium. The greater elasticity, greater speed, and directly proportional to the temperature. So if you want to speed up if you want to increase the speed of sound in hair, you just eat up the hair, you know. So so on a hot sunny day in the summer, when you shout, it travels much faster than a cold winter day where temperature is much less. All right. So we derive this formula for you, that the wave formula, the speed is equal to the frequency times the wavelength. But now I'm telling you that the speed varies with the elastic property of the medium, and the density, and the temperature, which is through. Okay. Um, Very important. I said it before. The speed of a wave in a medium is fixed. Keeping the temperature uh, fixed, of course. So the speed of, we said the speed of sound in here is about 340 meters per second. It kind of varies with the temperature, but it's relatively fixed. And the speed of sound in soft tissue is 1540 meters per second, which is fixed. So if you can somehow vary the frequency, then you have to vary the wavelength in order to keep the speed fixed. All right. So this is what I was saying to you before. The speed is inversely related to the elastic property. We call this the Young's modulus. So it's inversely related to Sorry, not inversely. It is directly related to the square root of the elastic property, the Young modulus. So the speed is directly proportional to the square root of the elastic property, and we call that Young's modulus. And it is inversely proportional to the density. The greater the density, the slower the speed. The less the density, the greater the speed. All right, and the, 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 the speed is also directly proportional to the temperature. Okay, all right. I mean, the only thing I'm going to say about boundary phenomena, because when you're doing ultrasound in the body, there are varying boundaries. You know, you have soft tissues, you have blood, you have bone, you have all that sort of stuff. So the different structures that the sound wave come across, you know, there's a boundary between those media. There's a boundary. So the only thing you need to remember is that if the sound wave is traveling from a less dense medium to a more dense medium, it's going to slow down. If it's traveling from a more dense medium to a less dense medium, it's going to speed up. The sound wave varies directly with the temperature. The greater the temperature, the greater the speed. And it varies inversely with the density, as we pointed out before, varies directly with the elastic property of the medium. So that's, you know, that's basically, we're not going to go into all of this, but again, the wave is reflected. Some of the wave is reflected, and some of the wave is going to be transmitted through the medium. Okay, so these are the summary of what, you know, I've been telling you. The wave speed is always greatest in the least dense medium because it varies inversely with the density of the medium. The wavelength is always greatest in the least dense medium, and that's from the same thing. The lower the density, the greater the speed. So the greater the speed, you know, the wavelength is gonna be increased. Very important, but frequency is not altered by crossing a boundary. So if the frequency is not altered and the speed is going to increase and decrease, then the thing that have to increase and decrease is the wavelength. Frequency is not altered by crossing a boundary. So if you're using a 2 megahertz transducer to do your ultrasound, the frequency in all the tissues are still going to be 2 megahertz. What is going to vary is the wavelength. So if you move from a more dense to a less dense medium and the wave speeds up, what's going to increase is the wavelength. The wavelength is going to increase. So these summaries are very important. So, and this is saying that the amplitude of the incident wave is always greater than the reflected wave. So if you think about it, when you have an incident wave, that's, you know, you produce your ultrasound vibration of the crystals, you produce your ultrasound, the ultrasound travels to the structure you're looking at. So incident, some of it is gonna reflected backwards, and some is going to be transmitted through the medium. We're talking about energy here. So if some of the energy passes through the structure and some come back, then, you know, the portion that is coming back, the energy is going to be less than the energy that started out in the first place. Okay, you can't, you know, energy cannot be created. It can only be converted from one form to the next. So the incidence pulse Okay, the incidence pulse, that is this ultrasound that you generate and strike the tissue. This this energy is always the greatest. And remember what we said about energy. The energy of the wave is directly proportional to the amplitude of the wave, or the amplitude square of the wave. So that is why you said the amplitude of the incident wave is always greater than that of the reflected wave. Okay? Because the incident wave is going to split up into a reflected wave, which is coming back to the transducer, and a portion which is transmitted through the tissue. So the energy of the reflected wave is going to be less than the energy of the incident wave, and the amplitude is directly proportional to the energy. Okay, so this summary is very important. Okay, for your understanding of uh, incident wave, reflected wave, and transmitted wave. So, the law of reflection is observed when we do waves. You know, the angle of incidence is equal to the angle of reflection. Okay, so the angle of incidence is equal to the angle of reflection. So the law of reflection is obeyed in waves. So again, if we look at the ultrasound as a wave, and the incident ray, when it strikes a boundary, so this boundary could be anything, it could be any tissue. This boundary could be any tissue, okay? This boundary right here could be any tissue. So the ultrasound wave comes and it strikes the boundary, okay? Some of the wave is gonna be reflected, and some of it is gonna be transmitted. Okay? What we're saying, the angle of incidence is equal to the angle of reflection. Okay? To get the angle of incidence, you drop a perpendicular, and from the perpendicular to the incident ray, that's the angle of incidence. Okay? So those phenomena still obeyed. So again, when you have your ultrasound wave, and say this is the boundary, it may be the heart structure, whatever it is, the incident ray, okay, that's the ray, that's the ultrasound that is generated when it strikes a tissue. Some of it is going to be reflected, and this is the reflected uh, wave that goes back to the transducer and is converted. That ultrasound is converted to an electrical signal, and that's what you see on the screen. Okay, and then some of this incident ray is going to be transmitted through the tissue. Okay, it's going to be transmitted through the tissue. So the energy again, wave is energy phenomenon. It's just an energy phenomenon. Wave transmits energy, and the amount of energy is related to the amplitude of the wave. So the energy possessed in this incident uh, ray or wave, some of it is going to be reflected and some of it is going to be transmitted. So the greatest energy is the incident ray. So the reflected ray energy is going to be less than that, and the transmitted wave is also the energy is going to be less than the incident uh, wave. So therefore, the amplitude of these two is going to be less than the amplitude of the incident ray. Okay. When a when a wave strikes a boundary, again we said some of it is going to be reflected, some of it is going to be transmitted through the second medium. The it's not going the the transmitted ray or wave is gonna be angled. It's not gonna come straight down. It's gonna bend. Okay, and this is what we call refraction. So the transmitted ray is going to bend depending on the density of the medium in which it is transported. So the refraction is just the bending of the transmitted wave when it passes from one medium to a next medium. Okay, that's what we call refraction. So all waves, so these are the properties of waves. All waves will, have an incident wave. All waves are capable of reflection, and all waves are capable of refraction. Okay, all waves gonna have a wavelength. All waves gonna have a frequency. All waves gonna have amplitude. So these are properties of waves. Okay, so it's important to understand that. So again, we went over reflection, refraction. All waves, in addition to incident, reflected, transmitted, refracted, all waves also diffract. All waves will have some amount of what we call diffraction. And when we talk about the diffraction of waves, it is the change in the direction of the wave as it passes through an opening or around a barrier in its path. Okay? So all waves, if you discover something and you say it's a wave, it has to have all these properties. If you can demonstrate that it has all these properties, then you're correct. It's a wave. Okay? So all waves can incident, can be reflected, can be refracted, and can be diffracted. Okay? So diffraction again is just a change in the direction of the wave as it passes through an opening or around a barrier in its path. So the amount of diffraction increases with increase in wavelength, and it decreases with decrease in wavelength. A simple way of looking at diffraction is if, say, you're in a big boat, you're in a ship. The water waves. Water. You have water waves. So if you're in a big ship, huge ship, uh, when the water wave comes up to the big ship, okay, so that is regarded as a barrier, okay. The waves are going to change direction. So when the water wave comes up to a barrier, it will change its direction. So a big ship, the water wave is going to change its direction, and the amount of diffraction increases with the increase in wavelength. For a huge ship, the wavelength is going to be huge. So anything in its path can be toppled over, okay? As opposed to if you have it's a very tiny boat, you're still going to have diffraction, but because the wavelength is much smaller, it will cause less disturbance. Um, so, all right. So again, if you have a barrier, okay, or a small opening, the wave will diffract. It's going to bend around it, okay? So it's going to change its direction, okay, as it passes through this. So the wave will, a barrier small, is going to change its direction, all right? So that's diffraction. So all waves have these properties. All waves have a wavelength, frequency, amplitude, have an incident wave which will reflect. It's going to reflect. It's going to be transmitted, and when it transmits, it's going to be you're going to have a refraction because if it moves from one medium to the next medium, it's going to refract, and it can also diffract. All right. So in addition to all that we spoke about, all waves interfere. All waves interfere. So when you have two or more waves traveling in the same media, they will interfere with each other. Okay? So when we talk about the interference of waves, it's what happens when two or more waves meet along the same medium. So a number of things can occur. Okay? You can have what we call constructive interference, or you can have destructive interference. When we spoke about speckle tracking echo, I don't know if you guys remember we did talk about constructive and destructive interference. Now we're going to look a little bit more into the science of this. Okay, so all waves will interfere with each other. So it is the phenomenon that occurs when two waves meet while traveling along the same medium. The medium takes on a shape that results from the net effect of the two individual waves upon the particles of the medium. So you can have what we call constructive interference. So these are two waves and they're traveling in the same medium. When they meet, if they meet nice like this, where crest meet crest, trough meet trough, crest meet crest, trough meet trough. So you have a nice constructive interference where the crest is now bigger than each of the incident wave, and the trough is also larger. So this is what we call constructive interference. So usually when you get constructive interference, depends on what you're talking about, it will give you something looking bright. Okay, so when we talk about speckle tracking echo, and we look at the grayscale, we look at the heart, the grayscale, you have different shades of gray. You have some bright and some dark. The bright speckles is due to constructive interference. The waves crest meet crest and trough meet trough. Okay, so you get nice bright speckles. And then this is destructive interference, where crest meets trough, crest meet trough. So they cancel out each other. So that give you it's dark. You get a sort of certain darkness. So that when we do speckle tracking echo, that's basically what we do. We look at the grayscale, and the grayscale is series of interference, destructive, constructive, destructive. So the bright speckles is due to constructive interference, and then the dark speckles due to destructive interference. All right, so constructive interference, uh, two inter- all right, for constructive interference, with constructive interference, the two interfering waves have a displacement in the same direction. Okay. All right. Somebody have noise in their background, please. Please pay attention to your noise in the background, please. Okay. So when we say constructive interference, two interfering waves have a displacement in the same direction. So we show you crest and crest, trough and trough, upward or downward displacement. The medium has a displacement that is greater than the displacement of the two interfering pulses. So when you look at the net result, it is greater than the two interfering pulse or waves. Okay, so that's what we call constructive. So constructive interference, you're just adding the waves together. It might not You might not have crest and trough and trough. It might be a little bit off, but if you do the summation, the net result is the amplitude is going to be greater than any one of the interferent waves. As opposed to destructive interference, the two interfering waves have a displacement in the opposite direction, and as a result, the displacement is less than the displacement of the largest amplitude wave. So again, when we talk about destructive interference, we have crest and trough, trough and crest. So they sort of cancel each other out. But you may not have the direct lining up of crescent and trough. It may be a little bit off, but when you do the summation, it's going to be less. So the principle of superposition is just adding the waves. Okay, so you might not get a destructive interference where you get a straight line, and a constructive interference where the amplitude is twice the amplitude of the interferent wave. But constructive and destructive interference, we use that phenomenon in speckle tracking echo. Okay, we use that in speckle tracking echo because the speckles, the speckles that we see in speckle tracking echo is as a result of interference. Okay, all waves have certain properties. All waves have frequency, have a wavelength, has a period, has a amplitude. You can have incident waves, you can have reflected waves, refracted waves. The waves can diffract and the wave interfere. So there was a there was a great debate about light because there are a few physicists who thought that light was not a wave, and there's a few physicists who say that light was a wave, but they, you know, of course, we said that all waves have these properties. And there's a famous Young experiment where Young showed that light is actually a wave because he showed that the light wave uh, interfere, and when it interfere, you can have destructive and constructive interference. So light was shown to be a wave by just doing the experiment, showing that light wave have all these properties. So we're gonna stop here, but you have to have a basic understanding of